Greetings dear conference members. I will present my work entitled A Transfer Learning Approach for Rapid Classification of Networks Traffic. Let's start with some introduction. Traffic classification is the process to categorize network traffic into relevant classes. A virtual private network offers businesses data confidentiality by establishing an end-to-end private tunnel over third-party networks. VPN is a serious obstacle for conventional traffic classification scheme. However, deep learning-based traffic classification frameworks are valued for their capability to reliably identify normal traffic as well as the VPN traffic without explicit feature search. Transfer learning is an effective way for knowledge sharing between two domains. In transfer learning, the weights from source model are assigned to the target model as initial weight. Here are some contribution of this work. We have employed transfer learning for traffic classification. For this, we trained source model and assign its weight to the target model as initial weight. The target model trained using transfer learning outperforms the baseline model trained from scratch in terms of time efficiency. Here we have the system model. In system model we have modules, the source module and target module. The source module has source model ms, which is trained on dataset ds. The target module has the target model, which is trained on the target dataset dt. Dataset ds contains flow-based time-related features with label space indicating both application level and VPN, non-VPN traffic characterization, while the target dataset contains flow-based time-related features with label space indicating VPN, non-VPN traffic classification only. Here we have the problem formulation. The source dataset has sample space indicated like this. The target dataset dt has sample space denoted like this. Here we can see that these x are the feature space and y are the label space. In here we can see that the feature space of the two dataset is same, but the label space of two dataset is different, as indicated in equation 1. The source domain is modeled like this, where this is a sample space and this is a marginal probability distribution of the source dataset, and this is the source task where we have the source predictive function. For the similarly for the target dataset we have the label space and the marginal probability distribution, and we have the target task, and this ft is the target predictive function. So we formulate our transfer learning problem as given the source domain with the source task and the target domain with the target task. We have to increase the learning accuracy of the target predictive function in target domain and decrease the corresponding training time tt using the knowledge from both the source domain and the target task, where the source and target domains are different, and similarly the source task and the target task are also different because they have the different label space. Here we explained the dataset use. We use the UNB VPN non-VPN network traffic dataset. It has the time related features, and there are 4 timeouts with time span like this, and there are 2 scenarios. Scenario B dataset has application level in addition to VPN non-VPN identification, and so this has the 14 classes, and this dataset is assigned to the source dataset. Scenario A dataset has VPN non-VPN traffic classification, so it has 2 classes, and this is assigned to the target dataset. So for pre-processing we use a z-score normalization for each timeout individually for both scenarios, and for the splitting for both the source dataset and target dataset, we assigned 80% of the samples as a training dataset, and the 20% of samples are assigned to the validation dataset. This table indicates the layered architecture for source model and the target model. We can see that the freeze layer of the target model are indicated here. So we first trained the source model ms on source dataset for 1000 epochs. So figure 2 illustrates the training and validation accuracy of the source model. Table 2 shows the performance metrics of the source model. We use the source model which has the maximum validation accuracy for for further processing. So afterward we assigned the weights of the source model to the corresponding layer of the target model MT and trained the trainable layer of MT on the target dataset. As a baseline, we also trained the baseline model MB on target dataset DT from scratch. The baseline MB has the same architecture as of the MT, except that all of its layers are trainable. MT and MB both are trained for 600 epochs. We selected the best model based on validation accuracy using callbacks. So in here, in figure 3, we can see that the target model gained maximum accuracy of 0.91 at the epoch 207, while the baseline model MD gained maximum accuracy of 0.84 at epoch 595. We can see that the target model has outperformed the baseline model for both validation and training accuracy. In here we measure the time for baseline model and the target model for 600 epochs, as well as reach the maximum validation accuracy. So we can see that for both 600 epochs and for the time to reach the maximum validation accuracy, the target model has outperformed in terms of training time. So table 3 illustrates the performance metrics of the base model and the target model on validation data set DV. We can see that the target model has outperformed the base model for all the performance metrics. To conclude, efficient traffic classification is significantly important for the quality of service in cognitive radio access network management. In this paper, we did transfer learning for traffic classification. The target model outperforms the baseline model in terms of accuracy, the number of iteration, and training time. This is the end of my presentation. If you have any question, you may ask.